Welcome back to the deep dive, part of the Neural Intel podcast. Have you ever looked at the incredible breakthroughs we're seeing in AI, things like image recognition, natural language processing, and just wondered, okay, how does it really work under the hood? Like, can we ever truly understand these systems, or are they always going to feel like a bit of a black box? We're talking, of course, about those huge leaps driven by deep neural networks, things like CNN's convolutional neural networks, which just, well, completely transform computer vision, and the transformer models that are pretty much everywhere now, totally redefining how we handle language. These architectures, they've given us unprecedented scale, amazing results across so many areas. They've really reshaped things.
You've definitely hit on a crucial point there. They have been revolutionary, no question. But for all that empirical success, all that widespread use, these neural networks come with a pretty significant list of well-known technical challenges. As a lot of recent research points out, they get criticized for having just immense parameter counts. We're talking billions sometimes. And this huge number of parameters, it's not just a number on a page. It means they need vast amounts of data, often data that's been painstakingly labeled. And that, in turn, demands really expensive compute resources, both for training and for running the models later for inference. Beyond that, there's that notorious lack of interpretability, or the black box issue you mentioned. Plus, they often have robustness issues baked in. It can be surprisingly tricky to predict how they'll react to even small changes in the input. And their ability to generalize, to work well on new data, that's not always guaranteed, which raises real concerns about reliability in critical situations.
Right. And that is exactly what we're going to dive deep into today. Our mission here is to explore a really powerful alternative way of thinking. Operator-based machine intelligence, a Hilbert space framework for spectral learning and symbolic reasoning. Now, we're going to keep our focus really tight today, strictly on the fascinating technical details, the implications of this advanced mathematical approach. So you won't hear us getting into ethical debates or inclusivity discussions this time around. Our lens is purely on the engineering, the math, the stuff that makes this kind of intelligence tick. As always, we want to give you that shortcut to being well-informed, focusing strictly on the how and the why from a technical angle.
Exactly. And you should expect this framework to, well, fundamentally redefine how we even think about learning. It's a shift away from the dominant idea, which is learning as just optimizing a finite, even if huge, number of parameters, like in most neural networks. Instead, this approach sees learning as sophisticated computation, as operator estimation within infinite dimensional function spaces.
Infinite dimensional function spaces. Right. Okay.
Yeah. And the promise here is pretty significant. We're talking inherent interpretability, potentially much better efficiency in certain cases, and strong theoretical guarantees that are part of the design from the start, not something you try to tack on or just hope for afterwards.
Okay, let's really unpack this. A fundamental shift, you said. Our current AI, especially deep learning, relies heavily on these finite dimensional parameter spaces.
Mm-hmm.
Can you maybe paint a clearer picture of just how massive these parameter counts really are in the big state-of-the-art models? Because I think for a lot of us, billions of parameters just sounds like, well, a huge abstract number.
It absolutely can feel abstract. Let's try to put it in perspective. Okay, so a typical CNN for image recognition, maybe something like ResNet, that might have tens of millions of parameters, already a lot, right?
Tens of millions.
But then you look at the transformer models, especially the large language models everyone's talking about. They can have hundreds of millions or billions of parameters. Take something like GPT-3. That one comes in at a staggering 175 billion parameters.
175 billion.
Wow. And this massive parameter count, it isn't just an impressive statistic. It directly means these models have a truly voracious appetite for data. They demand these enormous labeled data sets. Compiling them costs immense effort, time, money, and all those parameters, all that data, they gobble up equally expensive compute resources. For training and inference, you're talking about huge clusters of specialized GPUs running for weeks, maybe months, which leads to major inefficiencies. Energy use, cost, the time it takes to just develop and deploy these things.
So it's not just the size itself, but this huge resource drain that comes with it, like an insatiable hunger for data and power. And then there's this interpretability issue, which seems to pop up constantly when people critique deep learning. These black box function approximators, as they're often called, they just seem to hide their reasoning, don't they?
The term black box is incredibly apt, isn't it? Because even though they can be remarkably good at predicting things, understanding why a deep neural network makes a particular prediction or decision, that remains notoriously difficult. Think about a self-driving car's vision system, maybe using a CNN. if it misidentifies something important.
Like a stop sign.
Exactly. Or if a large language model generates a response that's just weird or wrong. It's incredibly hard to trace back through, billions of these interconnected weights and activation functions to figure out why it produced that specific output. There's just no clear human understandable chain of logic to follow. And that lack of transparency is a huge barrier, especially for high-stakes areas. Medical diagnosis, autonomous driving, financial modeling.
Places where you absolutely need to know why.
Precisely. You need accountability, trustworthiness, and it's this lack of clarity that really fuels the search for more principled, data-efficient alternatives that offer that transparency by design.
And it's not just about understanding why, but also about trust, right? If you can't fully grasp how a system works, how can you really guarantee it's reliable? Which brings us to these concerns around robustness and generalization. Even with all that data, all that compute, these models can sometimes be surprisingly brittle.
They can be, absolutely. Despite achieving high accuracy on specific benchmark tests, their robustness can be limited. You've probably heard about adversarial attacks.
Yeah, where tiny changes to the input cause huge errors.
Exactly. A slight, almost imperceptible change to an image adding tiny amounts of noise can cause a model to completely misclassify something obvious, like mistaking that stop sign for a speed limit sign, maybe. Their ability to generalize can also be fragile sometimes, or at least hard to guarantee without very specific theoretical backing. They might perform brilliantly on the data they were trained on, but then struggle significantly when they encounter data that's even slightly different from what they've seen before.
So, out of distribution data, as they call it.
Right. And this inherent fragility means their real-world usefulness can be limited, especially in dynamic, unpredictable environments where you absolutely need to trust their consistency and reliability.
Okay, so we're seeing these incredible capabilities from deep neural networks, truly pushing the limits of AI, no doubt about that. But underneath, there are these persistent technical challenges, these resource drains, those massive parameter counts, the interpretability problem, the robustness concerns. It really does make you wonder, doesn't it? Is there a fundamentally different way to approach machine intelligence? One that tackles these issues head on, instead of just trying to patch them up or build even bigger, more complex models?
That's a great question, and it's exactly the question that leads us to this alternative paradigm we're discussing today. Instead of just scaling up complexity in neural networks, this framework suggests we take a step back. We reimagine learning from first principles, grounding it deeply in functional analysis.
Okay, so let's talk about that foundation, the Hilbert space framework. Now, for many of us, Hilbert space sounds, well, pretty intimidatingly mathematical, maybe a bit abstract. Can you give us a clear, maybe accessible definition? Perhaps use some analogies to help us really get a handle on what it is?
Of course. Let's try to demystify it a bit. At its heart, a Hilbert space is a vector space. That just means you can add things together and multiply them by numbers, just like regular vectors in 2D or 3D.
Okay, standard vector stuff, addition, scaling.
Right. But the crucial addition is an inner product. This inner product is what lets us define concepts like length, distance, and angle. Or more generally, how similar two things in the space are, or if they're orthogonal, like perpendicular lines.
Like a dot product, but maybe more general.
Exactly like a generalized dot product.
Yeah.
And the final key property is completeness. Completeness essentially means the space has no holes in it. If you have a sequence of elements, say functions, that are getting closer and closer together, they're guaranteed to converge to something that still lives within that same space.
Ah, okay. So it's like a space with no missing pieces, no weird gaps you could accidentally fall into if you follow a converging sequence.
Precisely. If a sequence looks like it should converge to something, that something is guaranteed to be in the space. Maybe the best analogy is to think of it as an infinite dimensional playground for functions. Instead of vectors with, say, 3 components, x, y, z, you're dealing with functions. And functions can be thought of as having an infinite number of components or values, representing continuous things.
Like a sound wave.
Exactly. Examples like L2R, the space of square integral functions, common in signal processing. Think of signals where the total energy is finite, like sound waves or electrical signals. Or A2, the space of square summable sequences, crucial in digital signal processing, like the sequence of samples from an audio recording. These are spaces where you can meaningfully measure distance and angle between functions, just like you do with everyday vectors, but for much more complex objects.
Okay, so instead of a data point being just a row in a spreadsheet or a grid of pixels, you're saying the big conceptual leap here is to treat data signals, images, whatever, not as finite lists of numbers, but as actual functions that live inside this huge, infinite dimensional Hilbert space.
Precisely. That's the foundational shift. Instead of viewing data as finite dimensional vectors, which is, the standard way in most machine learning today, this paradigm sees them as continuous functions. An image isn't just pixels, it's a function mapping coordinates, x, y, to color intensity. A time series isn't just numbers, it's a function showing how a signal changes over time, t. And these functions exist and operate within this very structured, mathematically rigorous world of a Hilbert space.
Okay. And if data are functions, then learning can't be about finding the right numbers, the right parameters for a model in the usual sense. It must be about finding something else, something that acts on these functions. What is that something else we're trying to find?
That something else is an operator. This is really the bedrock of the whole framework. Learning becomes identifying bounded, linear, or compact nonlinear operators that act on these functions. These operators are essentially transformations. They map one function to another function.
So like a mathematical machine that takes a function as input and spits out another function.
Exactly. They might encode transformations, like, say, a denoising operator that takes a noisy function and outputs a clean one. They could be regressors, take an input function, predict an output function, or even generators that create entirely new functions based on some input. So the learning problem gets reframed. It becomes inverse operator estimation, figuring out the operator T that explains the input-output pairs, FG you've observed, so TFG. Or it could be seen as a regularized projection problem or even spectral decomposition. These are all concepts with deep roots and well-understood properties in functional analysis. What's truly fascinating here, and I really want to stress this, is that this framework isn't just some minor adjustment to current models. It's really a return to fundamental mathematical principles. It leverages robust tools from functional analysis, classical signal processing, spectral theory, fields with decades of rigorous development. It's about building intelligence on a foundation where desirable properties like well-posedness, meaning a problem, has a unique, stable solution that depends continuously on the input data and stability, meaning small input changes only cause small output changes are inherent properties.
Built in from the start, not bolted on later.
Exactly. It's not just about finding what works through trial and error. It's about analytically understanding why it works and building that understanding right into the core of the system.
Okay, so it sounds like this isn't entirely brand new territory, but maybe a powerful reimagining or resurgence of some classical ideas. Can you trace those historical threads for us? What kind of legacy does this framework build on?
It definitely builds on solid mathematical ground that's been around for a long time. A key historical connection is to reproducing kernel Hilbert spaces, or RKHS.
Ah, kernels, like in support vector machines.
Precisely. RKHS provided the mathematical foundation for powerful early machine learning methods like support vector machines, SVMs, and kernel regression. These methods allowed us to implicitly map data into very high-dimensional, even infinite-dimensional feature spaces, and then perform linear operations there. They basically showed how learning could be done in function spaces long before deep learning really took over. They laid crucial groundwork.
And it sounds like this framework is also breathing new life into classical signal processing tools. Things like Fourier transforms, wavelets. These aren't new, right? But now they're becoming central to modern machine learning.
Absolutely. This approach is revitalizing and recasting classical signal processing tools. Fourier analysis, wavelet decompositions, integral operators. These are tools that, for decades, were mainly used in fields like electrical engineering, analyzing audio, images, maybe even quantum mechanics.
Right, things you learn in engineering school.
Exactly. Now, they're becoming core components of machine learning itself, not just pre-processing steps, but integral parts of the learning architecture. Take wavelet domain methods pioneered by people like Stefan Mallet. They provide stable, multi-resolution views of signals that are inherently robust to shifts and deformations. These aren't just mathematical nice-to-haves. They have direct, powerful consequences for how we process and understand complex data.
So we're taking these robust, well-understood mathematical tools and weaving them into a new kind of learning architecture. But what about modern innovations? What's genuinely new here compared to just applying those classical methods straight out of the box?
That's where the really novel computational and architectural innovations come into play. This framework introduces elements that go beyond just reapplying classical methods. We're seeing things like differentiable basis selection mechanisms, The system itself can learn which mathematical basis functions are most useful for a specific task, rather than us having to guess or pre-specify them.
So the model chooses its own tools.
In a sense, yes. Then there are learnable spectral nonlinearities. Things like adaptive soft thresholding or gain phase modulation in the frequency domain. These allow the model to adaptively filter or reshape frequency components based on the data. And we have these operator regression models, which generalize core deep learning concepts like convolutional layers or attention mechanisms, but define them rigorously within the function space. This ensures that theoretical grounding, that stability right from the beginning, instead of trying to analyze or impose it on a complex, empirically derived neural network afterwards.
That's really interesting, this idea of a return to these methods. It suggests they weren't always as prominent as maybe deep learning is now. It makes me wonder, if they're so theoretically elegant, what held them back? What were the practical hurdles or maybe shifts in research focus that allowed deep learning to surge ahead? And what's bringing them back into the spotlight now? The papers often focus on the what, but maybe less on the why of that historical ebb and flow.
That's a fantastic point, and it's something the papers often don't explicitly detail. While the theoretical beauty of these Hilbert space methods was recognized for a long time, practical implementation and crucially scalability were major roadblocks. Historically, the computational power and the specific hardware needed weren't really optimized for these kinds of infinite dimensional computations or complex spectral transforms, especially at the scale of modern datasets.
They weren't GPU friendly back then.
Not in the same way, no. Deep learning, on the other hand, with its heavy reliance on relatively simple matrix multiplications and convolutions, turned out to be perfectly suited for the parallel processing power of GPUs when they became widely available. The big data explosion was also a huge factor. When you suddenly have massive amounts of labeled data, the data hungriness of deep networks became less of a bottleneck, and their ability to learn features automatically end-to-end often outperformed methods that relied on handcrafted features or fixed basis functions.
Okay, so it was really a confluence of practical compute power and data availability that gave deep learning that massive boost.
Exactly. But what's fueling the resurgence now? I think it's a mix of things coming together. First, there's a growing awareness of deep learning's own limitations, that black box problem, the brittleness, the sheer resource cost we talked about. That created a real hunger for more principled, robust alternatives. Second, huge computational advances. Optimized numerical linear algebra libraries, highly efficient FFTs, and wavelet transforms running on GPUs. These have made the methods far more practical and scalable than before.
The tools caught up.
Right. Third, there's been a much deeper theoretical understanding of how to make these spectral methods learnable and differentiable, so they can be plugged directly into modern ML pipelines using frameworks like PyTorch or TensorFlow, which wasn't easy before. Think of those learnable spectral linearities we mentioned. And fourth, I think there's a growing realization that maybe one size doesn't fit all. For certain domains, physics simulations, medical imaging, complex signal processing building, and prior knowledge through these operator-based structures can be way more efficient, robust, and interpretable than just throwing a giant general-purpose neural network at the problem. So it's less one single breakthrough and more a maturation of the hardware, the software libraries, and the theory, all making these elegant ideas practically powerful again.
That really paints a clear picture. The tech landscape finally caught up to the theoretical elegance in a way.
Okay, now let's get into the core mechanics. We've defined Hilbert spaces, but how do we actually do things in them? Let's start with something that sounds fundamental. Orthogonal projection. Can you break down this idea of orthogonal projection onto a closed subspace? What does it mean geometrically?
Certainly. Let's try to make this concrete. Think about regular 3D space. If you have a point just floating above a flat tabletop, the orthogonal projection of that point onto the table is simply the spot directly underneath it on the table surface.
Like it's shadow cast straight down. Exactly. Casting a shadow at a perfect 90-degree angle. In a Hilbert space, it's the exact same idea, but applied to functions instead of points. Given a function f in our Hilbert space H and a closed subspace V with an H, think of V as a well-behaved collection of functions that itself forms a nice vector space. The orthogonal projection finds the unique function within that subspace V that is closest to our original function f. Closest here means minimizing the distance, as measured by the inner product. Mathematically, you're finding the function v in the subspace V that minimizes the squared norm or length of the difference fv.
Okay, so it's like finding the best possible approximation of our function f, but restricted to only using functions from that specific subspace V.
Precisely. And the defining property is orthogonality. The error, or residual, the difference between the original function f and its projection v, is orthogonal to every single function in that subspace v. This concept beautifully generalizes Euclidean projections to infinite dimensions, and it's fundamental to variational formulations in learning. Things like least squares regression and regularization often boil down to projecting data onto some subspace defined by the model's features or constraints.
And related to this, you mentioned functional approximation using bases. How do these orthonormal bases help us represent functions in these, well, still intimidating infinite dimensional spaces?
They do seem tempting, but orthonormal bases are the key to making them manageable. Because Hilbert spaces are vector spaces, they support orthonormal bases. Think of these as fundamental building blocks, like the 1000, 0, 0, round 1 vectors for 3D space.
Or sines and cosines in Fourier analysis?
Exactly. Any function f in a Hilbert space H can be written as an infinite sum of these basis functions, each multiplied by a specific coefficient. This is often called a Parseval expansion, and it's incredibly powerful. It means even a very complex-looking function can be broken down into a sum of simpler fundamental pieces. Each coefficient tells you exactly how much of that specific basis function is present in the original function f. This gives us compact representations, especially if many of those coefficients are very small, or zero, meaning the function is sparse in that basis. And this forms the foundation for many learning algorithms through truncation, just keeping the most important basis functions or thresholding, setting coefficients below a certain value to zero. These are absolutely vital for spectral learning and for ideas like compressed sensing, which we should definitely get into.
Okay, these concepts, projection, approximation using bases, they clearly sound like the essential mathematical building blocks. But how do we bridge the gap from these fundamental ideas to actually doing machine learning? Like predicting an output from an input or classifying data? Where does the learning part come in?
That's a fantastic transition, because this is precisely where the idea of learning as operator estimation takes center stage. It's really the core concept of this whole Hilbert space framework for machine learning.
All right, so tell us about this formal approach. How is the operator estimation problem actually set up mathematically?
Okay, so remember, we're thinking of data as functions living in Hilbert spaces. In a typical supervised learning scenario, the problem becomes identify a specific operator t that maps an input function, let's call it f from some input Hilbert space hx, to an output function, g, in an output Hilbert space hy, such that tf is a good approximation of the true g. This reframes the learning task as solving what's called a regularized empirical risk minimization problem.
Okay, that sounds like a mouthful. Regularized empirical risk minimization. Can you break that down into simpler terms for us? What are we actually trying to minimize?
Absolutely. Let's unpack it. The goal is find the best operator t. The objective function we minimize usually has two main parts. The first part is the empirical risk or data fidelity term. It simply measures how well our current operator t works on the training data we have. For each input function phi in our training set, we apply t to get a prediction t phi. Then we measure the difference between that prediction and the actual target output function guessed using the norm, distance squared, in the output space hy. We sum up these errors across all our training examples.
So it's basically a measure of how wrong the operator is on the training data, like a sum of squared errors, but for function.
Exactly like that. Conceptually, very similar to least squares error in standard regression. The second part is the crucial regularization term. It's there to prevent overfitting, to keep the operator t from becoming too complex or too tailored to just the training data. This term usually involves a balancing parameter, often called lambda, multiplied by some measure of the size or complexity of the operator t itself.
Okay, and how do you measure the size of an operator in infinite dimensions? For matrices, we have things like the Frobenius norm. Is there an equivalent here?
There is, and a very natural one. A common and powerful choice for regularization is the squared Hilbert-Schmidt norm of the operator, written as T2S. This Hilbert-Schmidt norm is a beautiful generalization of the Frobenius norm from finite matrices to infinite dimensional operators.
Ah, okay.
It effectively measures the energy or overall magnitude of the operator across all possible inputs. It provides a way to penalize operators that are too large or fluctuate wildly. And mathematically, the set of Hilbert-Schmidt operators actually forms a Hilbert space itself, which is a really nice property that makes the optimization problem well-behaved and often computationally tractable. It keeps the infinite dimensional problem grounded.
So it's a way to control complexity, to encourage simpler solutions, but operating directly on these function-to-function transformations rather than just tweaking individual weights in a neural net. That sounds incredibly elegant.
It really is. And this whole formulation is very powerful. It neatly generalizes classical methods like linear regression and kernel ridge regression, extending them to handle function-valued data. It also encompasses a wide range of learning paradigms under one theoretical roof.
Huh.
Integral operator learning, spectral filtering methods, Koopman operator learning we'll talk about later, even Gaussian process regression can be viewed this way. A major advantage here is the resulting mathematical transparency, interpretability, and rigor. Unlike the often opaque, iterative, non-convex optimization of deep neural networks, this operator-based view frequently leads to closed-form or variational solutions.
Meaning you can sometimes just calculate the answer directly.
Yes, or find it by solving a well-defined optimization problem with strong guarantees. This gives you a much clearer insight into why the learned operator behaves the way it does.
That level of mathematical clarity is really appealing. Now let's connect this theoretical elegance back to practical computation. We mentioned reproducing kernel Hilbert spaces, RKHS, earlier. How do they act as a bridge? How do they make working in infinite dimensions practical?
RKHS are absolutely fundamental in making these ideas computationally feasible. Their defining feature is the reproducing property. What this means, in simple terms, is that you can find the value of any function f in the space at any point x just by taking an inner product. You take the inner product of f with a special function associated with that point x, which is generated by the reproducing kernel, often written as kx, kx, ax, s, sk.
So the kernel acts like a probe.
Exactly. And the kernel function itself, kxx, basically acts as a similarity measure between points x and x. It implicitly maps your data into potentially a very high-dimensional feature space and computes the dot product there without ever needing to explicitly calculate those features.
So the kernel is doing a lot of the computational heavy lifting, defining similarities, and letting us evaluate functions almost by magic.
It feels a bit like magic, yeah. But the real computational breakthrough that makes RKHS so practical, even when dealing with infinite dimensions, is a theorem called the representer theorem. This is a key aha moment in kernel methods. It states that for a very broad class of learning problems set up in RKHS specifically, those involving minimizing a data fit term plus a regularization term based on the RKHS norm, just like we discussed the optimal solution function f. Even though it theoretically lives in an infinite dimensional space, it must lie in the finite dimensional span of the kernel sections evaluated at the training points.
Whoa, okay. Slow down. Finite dimensional span. What does that mean practically?
It means the optimal solution function fx can always be written as a simple weighted sum, fx or x, where the sum is only over your n training data points of Ania. So instead of searching through an infinite dimensional space, you only need to find a finite number of coefficients, the IEs.
That does sound like a magic trick. You start with an infinite problem, and this theorem just hands you a finite solution on a silver platter. Is there a catch? Any trade-offs?
It's not entirely a free lunch, but it's an incredibly efficient one. It brilliantly reduces what seems like an intractable, infinite dimensional optimization down to solving for a finite set of coefficient size. This is why kernel methods like SVMs and kernel ridge regression became so successful. For kernel ridge regression, for instance, this leads to a direct, closed-form solution for the coefficient size. You can calculate them using matrix inversion involving the kernel matrix K, or K guess I else J, and the regularization parameter O. And it's the core idea behind the famous kernel trick in SVMs, allowing them to find complex nonlinear decision boundaries by only computing these kernel values, inner products in the feature space, without ever explicitly representing that potentially infinite dimensional space.
So the main potential catch might be calculating or storing that kernel matrix if you have a massive number of data points.
Exactly. The kernel matrix K is nxn, where n is the number of training samples. If n is huge, computing or inverting, k plus y, can be computationally expensive, but there are many approximation techniques like Nystrom methods or random Fourier features developed over the years to handle large-scale kernel methods.
Okay, that's a truly ingenious way to make infinite dimensions manageable. Now, moving from these potentially continuous functions back to the discrete data we usually get from sensors or measurements, how do concepts like sampling and reconstruction fit into this Hilbert space picture?
This is absolutely critical for connecting the beautiful theory to the messy reality of real-world data. We talked about orthonormal bases and the Parseval expansion, FDEA. Its twin concept is Parseval's identity, F. This identity says that the total squared energy or norm of the function f is equal to the sum of the squared magnitudes of its spectral coefficients.
Energy conservation, basically.
Exactly. It highlights that the spectral domain, the set of coefficients, contains complete and equivalent information about the function. No information is lost in the transformation, just represented differently.
Okay, so the spectral coefficients hold all the information. How does that relate to sampling?
It leads directly into generalized sampling theory. This theory shows how functions can be perfectly reconstructed from a set of linear measurements, like samples. Crucially, it allows the analysis frame, the functions you use to take the measurements, and the synthesis frame, the basis functions you use for reconstruction, to be different, as long as they satisfy certain conditions, like being biorthogonal or forming frames.
So you don't have to measure and rebuild with the exact same tools.
Right. This decoupling is incredibly powerful in practice. Think about medical imaging like MRI or CT scans. The way data is acquired, measured, is very different from the mathematical basis used to reconstruct the final image. Generalized sampling theory provides the mathematical foundation for why this works.
And then there's compressed sensing. That sounds like a real efficiency play, getting more information from fewer measurements.
It absolutely is. It's a more recent and incredibly powerful extension of sampling ideas. Compressed sensing theory shows that you can achieve accurate reconstruction of signals from far fewer measurements than traditional Nyquist sampling would suggest.
The Nyquist rate being the classical minimum sampling frequency.
Yes. Compressed sensing says you can often beat Nyquist significantly, provided the signal has a special property. It must be sparse in some dictionary or basis. This means the signal can be represented accurately using only a few non-zero coefficients when expressed in the right basis, like wavelets for images or Fourier for certain periodic signals.
So if the signal is simple in the right language, you don't need as many measurements.
Precisely. You then recover these few non-zero coefficients by solving an optimization problem, typically involving minimizing the ANO norm of the coefficient vector, subject to the constraint that the reconstructed signal matches the measurements you took. The OR norm has this amazing property of promoting sparsity. It naturally pushes most coefficients towards zero. And successful recovery is mathematically guaranteed under certain conditions on the measurement process, most famously the restricted isometry property, or RIP.
The restricted isometry property, RIP, that sounds very technical again. Can you give us a more intuitive feel for what RIP actually guarantees?
Let's try. Think of RIP as a guarantee that your measurement process doesn't accidentally squash the important information about the sparse signal. It ensures that when you take those limited measurements, fewer than Nyquist would demand, the distances between different sparse signals are approximately preserved in the measurement space.
So it doesn't make two different sparse signals look the same after measuring.
Exactly. It prevents the measurement process from confusing distinct sparse signals. If the measurement matrix satisfies RIP, it means that the scar structure of the underlying signal is maintained well enough through the compression measurement process that you can uniquely and accurately recover the original sparse signal later using Euro-minimization. It's like having a guarantee that your compressed snapshot retains enough distinct detail to perfectly reconstruct the original sparse scene.
Okay, so you're essentially finding the simplest, sparsest explanation that fits the limited data you have. And how does this connect back to machine learning in a practical way?
In machine learning, these sampling and sparsity principles offer principal strategies for feature extraction, dimensionality reduction, and regularization. Instead of just learning millions of parameters from scratch, models can be designed to operate on sparse, band-limited, or frame-constrained representations. This means we can build strong structural priors directly into our models, based on assumptions like sparsity. This often leads to better generalization, especially with limited data, improved computational efficiency, and sometimes even inherent robustness. For instance, spectral filtering techniques we'll discuss, like thresholding coefficients, become natural forms of regularization operating directly in the function space, encouraging simpler, sparser solutions.
Right. Now, compressed sensing sounds incredibly powerful, especially the theoretical guarantees like RIP. But I imagine there are practical aspects the papers might not always emphasize. What about the real-world difficulty of actually proving that RIP condition holds for complex, high-dimensional data? That seems hard. And what about the computational cost of solving those minimization problems at the massive scale of modern AI, especially if the dictionary or basis itself is very large or needs to be learned?
That's a very insightful point, and it highlights some significant practical challenges that aren't always front and center in the theoretical discussions. First, proving the restricted isometry property for arbitrary, real-world measurement matrices in dictionaries. That's extremely challenging, often practically impossible to do analytically. RIP is typically proven for specific constructions, like random matrices, Gaussian, Bernoulli, under certain conditions on sparsity and dimensionality. For real-world sensing matrices or learned dictionaries, you usually can't rigorously prove RIP holds.
So practitioners often rely on heuristics or empirical results instead.
Often, yes. Or they rely on the fact that many random constructions satisfy RIP with high probability and hope their practical setup is random enough. Second, the computational cost of a minimization. While the problem is convex, and we have efficient algorithms like FISTA, ADM, basis pursuit, solving it for very high-dimensional signals and large dictionaries can still be computationally demanding, potentially slower than simpler methods if sparsity isn't extremely high. And third, if the dictionary A itself is learned adaptively, as in dictionary learning, the problem often becomes non-convex and much harder to solve globally. You might get stuck in local minima. So yes, while the theory is elegant and powerful, translating compressed sensing into robust, large-scale practical systems involves significant engineering effort, algorithmic choices, and often compromises or assumptions that aren't fully captured by the clean theoretical guarantees alone.
That makes perfect sense. Theory provides the ideal map, but the real-world terrain always has unexpected obstacles. Okay, with that grounding, let's move on to see how this theory translates into specific architectures and their empirical success. Let's start with Fourier models. They seem foundational in spectral learning. How are they represented mathematically and used here?
Fourier models are really the classic example of using an orthonormal basis in a Hilbert space. Let's consider a function f in L2 ILO. That's the space of square integrable functions on the unit interval. Think of a simple, finite duration continuous signal. The classical Fourier series represents this function fx as an infinite sum, fx e of fuga x e2 5x. Those ei2kx terms are the complex exponential basis functions, essentially sines and cosines of different frequencies k.
And the fuck are the Fourier coefficients.
Exactly. The Fourier coefficients Fock tell you the amplitude and phase of each frequency component k present in the original signal f. They're calculated by integrating fx against each basis function. And as we mentioned with Parseval's identity, the total energy fx is equal to at Fock, confirming that the spectral domain, the set of x, contains all the information.
Okay, so we can represent the function using these frequency coefficients. How do transformations or learning happen in this Fourier domain? You mentioned spectral filtering seems key.
Yes, spectral filtering is the core mechanism, and it's remarkably elegant. In this framework, transformations are performed simply by applying multiplicative weights, let's call them oak, directly to the spectral coefficients. So if Fock are the Fourier coefficients of the input function f, the coefficients of the output function g are just nook, Fock. You just multiply each frequency component by a specific weight.
Just multiplication, that seems simple.
It seems simple, but it's profound. This operation, which is just a diagonal operator in the Fourier domain, multiplying each component independently, corresponds exactly to the operation of convolution in the spatial domain. Mathematically, gxLhx, where the Fourier transform of the convolution kernel h is precisely that sequence of weights.
Wow. So convolution, which is fundamental to CNNs, is just multiplication in the frequency domain.
Precisely. This is the convolution theorem. It's a cornerstone of signal processing, and it means you can implement convolutions very efficiently using fast Fourier transforms, FFTs. Instead of sliding a kernel across the input spatial domain, you FFT the input, FFT the kernel, multiply the results element-wise, spectral domain, and then inverse FFT back. For large kernels, this can be much faster.
That equivalence is powerful. And what about interpretability and regularization using the spectral view? Does it offer advantages?
Huge advantages. Spectral filtering is inherently interpretable. When the filter brick is designed to be band-limited, meaning it sets weights for high frequencies to 0 or near 0, it directly suppresses high-frequency components.
Which means smoothing the signal, right? Removing sharp details or noise.
Exactly. This acts as a very natural form of regularization, encouraging smoother solutions and preventing the model from fitting noisy high-frequency variations in the training data. And if these filter weights are learned by the model, the system can adapt to emphasize discriminative frequencies relevant to the task. For example, in image classification, the model might learn to boost mid-range frequencies important for texture or low frequencies for overall shape. You can literally plot the learned filter book and see which frequencies the model thinks are important.
And this isn't just theory anymore. You mentioned a modern resurgence. Where are we seeing Fourier-based models making an impact in cutting-edge AI right now?
Indeed, it's happening now. A prime example is the Fourier neural operator, FNO. These architectures build neural networks entirely in the spectral domain. They learn transformations by learning those spectral filter weights FNs. FNOs have proven remarkably effective for learning complex mappings between infinite dimensional function spaces. A key application area is solving partial differential equations, PDEs.
Like simulating fluid flow or weather prediction?
Exactly. Simulating complex physics like fluid dynamics, heat transfer, material science. FNOs can often learn to predict the solution of a PDE much faster than traditional numerical solvers. They're being used in physics-informed neural networks where the known equations of physics can be incorporated as constraints or regularization. And they're even showing up in graph neural networks, where the graph Laplacian spectrum, related to Fourier analysis on graphs, can encode important structural information. It really shows how these classical tools are being powerfully re-engineered for today's hardest AI challenges.
It's truly remarkable how such a classic mathematical tool, something many of us encountered in basic engineering or physics, is being repurposed for the absolute cutting edge of AI. Okay, Fourier analysis is great for global frequency content, assuming things are somewhat periodic. What if our data isn't nicely periodic? Or what if we need to focus on features that are very localized in time or space, rather than just global frequencies? Signals often have short bursts, sharp edges, non-stationary behavior. A global Fourier view might miss those.
That's an excellent point, and it's exactly where wavelets come in. Wavelet transforms provide a powerful alternative to Fourier analysis, precisely because they decompose functions into basis functions that are localized in both space or time and frequency or scale.
So they have good resolution in both domains.
Exactly. Unlike Fourier's sine and cosine waves, which are perfectly localized in frequency but spread out over all spacetime, wavelets are designed to be compact in both domains. Think of them as small, oscillating wavelets or wave packets. They can be stretched or compressed, scaled, to capture broad, low-frequency features or sharp, high-frequency details. And they can be shifted, translated, to pinpoint exactly where or when those features occur in the signal. This gives them a zoom-in, zoom-out capability across different scales and locations that Fourier analysis lacks.
Okay, so how are these wavelet families actually constructed to get that dual localization?
Typically, you start with a single prototype function called the mother wavelet, often denoted CANX. This function is designed to be oscillatory and have finite energy, and importantly, its average value is 0. Then, a whole family of wavelets, CANX, is generated by simply scaling and translating this mother wavelet. CANX. Here, J is the scale parameter. Larger J corresponds to coarser scales, lower frequencies, smaller J to finer scales, higher frequencies. And CANX is the translation parameter, determining the wavelet's position in space or time. This multi-resolution decomposition makes wavelets incredibly effective at capturing sparsity in signals that have localized features or sharp transitions, like natural images. It's why they form the basis for compression standards like JPEG 2000 and are widely used for denoising and analyzing non-stationary signals.
Right. And building on wavelets, there's something called scattering transforms. This sounds like a key innovation discussed in the source material. What's special about them? Why are they important?
Yes, Stefan Milat's scattering transforms are a really fascinating development stemming directly from wavelet theory. They're often described as a form of non-learned deep feature extraction, which sounds a bit paradoxical maybe.
Non-learned deep features. How does that work?
The core idea is elegantly simple but powerful. It involves recursively convolving the input signal with a bank of wavelet filters at different scales and orientations, and then applying a nonlinearity, specifically the modulus absolute value operator, at each stage. So the first layer computes things like FQ11. The second layer computes things like FJ1, FJ2, essentially applying wavelets to the output of the previous layer. This builds up a hierarchy of features, SGA, where each scattering coefficient captures different types or combinations of signal variations across multiple scales and spatial locations. It mimics some properties of deep convolutional networks, but the filters, the wavelets, are fixed and analytically defined, not learned from data.
Okay, fixed filters. And crucially, you mentioned they have remarkable theoretical guarantees.
Exactly. This is where scattering transforms really shine. They come with strong, provable mathematical properties. They're inherently translation invariant, meaning if you shift the input signal, the scattering coefficients, the extracted features, don't change, which is great for object recognition, for instance.
Makes sense.
They are deformation stable. Small warps or stretches in the input signal only lead to small changes in the output features. This provides inherent robustness. They also preserve signal energy in a structured way. And, importantly, they are mathematically proven to be Lipschitz continuous to small deformations.
Okay. Lipschitz continuous to small deformations. That sounds like a very strong robustness guarantee. Can you unpack what that means for someone maybe not familiar with the term?
Sure. Think of it like this. Lipschitz continuity puts a strict upper bound on how much the output can change for a given change in the input. In this context, it mathematically guarantees that if your input signal undergoes a small, smooth deformation, like slightly rotating a digit image or slightly stretching a texture pattern, the corresponding scattering coefficients will also change only by a small amount, and that amount is predictably bounded by the size of the input deformation.
So no sudden catastrophic changes in the features for small input variations.
Precisely. It means the representation is inherently stable and predictable under these common types of real-world variations. This is invaluable for building reliable systems, a stark contrast to the potential fragility of some deep learning models to adversarial or even just natural perturbations.
That sounds incredibly robust by design. How do they actually perform in practice, empirically? Theoretical guarantees are great, but do they hold up against, say, trained deep learning models on real tasks?
The empirical performance is actually quite impressive, especially considering the features aren't learned. The source material highlights results like on the curate texture dataset. Using just the scattering coefficients fed into a simple linear SVM classifier, they achieved 98.6% classification accuracy. That's highly competitive, outperforming many handcrafted feature descriptors and getting close to the accuracy of complex, trained CNNs designed for texture analysis.
Wow, with just a linear classifier on top.
Yes. And for the timid speech phone recognition task, scattering features were fed into a simple multi-layer perceptron, MLP. The results were competitive with deep CNNs, specifically designed for speech. But, and this is key, the scattering-based model used far fewer parameters and showed greater robustness to noise and pitch variability.
So competitive accuracy, fewer parameters, better robustness, and you mentioned they don't require backpropagation.
Exactly. That's another huge advantage. Because the wavelet filters are fixed and analytically defined, and the nonlinearity, the modulus, is also fixed, these models do not require backpropagation or gradient descent for feature extraction. This translates to significantly lower training costs and improves reproducibility. You just compute the scattering transform once, then train a simple classifier like an SVM or small MLP on the resulting features.
That's a massive difference from training a deep network for days or weeks.
Absolutely. And those provable stability bounds against deformations aren't just theoretical niceties. In critical applications, medical imaging analysis, fault detection in machinery, maybe even autonomous navigation where reliability and robustness are paramount, having that analytical guarantee is invaluable. It provides a level of trust that's often hard to achieve with purely empirical deep learning models, which might work great 99% of the time but fail unexpectedly and inexplicably in that crucial 1%. It's a foundational difference in approach.
Okay, from static signals like images and textures, let's shift gears to dynamics. Another fascinating area mentioned is Koopman operator learning. This seems like a completely different approach, aimed at modeling nonlinear dynamical systems. How does it manage to seemingly linearize what feels like a fundamentally nonlinear world?
The core idea behind Koopman operator learning is really quite elegant, almost a philosophical shift in perspective. Instead of trying to directly model the complex, often chaotic, nonlinear evolution of a system state X over time, it aims to find a way to describe the evolution of functions of the state, called observables, using a linear operator.
Okay, functions of the state, what does that mean?
Imagine tracking a complex fluid flow. Instead of tracking the position and velocity of every single particle, the state X, which evolves nonlinearly, maybe you track simpler quantities derived from the state, like the average temperature in a region, the total kinetic energy, or maybe more complex functions. Let's call such a function Gx. The Koopman operator framework posits that there exists an infinite-dimensional linear operator, K, that perfectly describes how the value of any such observable function, Gx, evolves over time. Specifically, gxt plus 1 equals kgxt.
So the evolution of the observables becomes linear, even if the underlying state X evolves non-linearly.
Exactly. You lift the dynamics from the original nonlinear state space into a potentially infinite-dimensional function space, a Hilbert space of observables. And in this lifted space, the dynamics become linear, governed by the Koopman operator K. This is incredibly powerful because we have a vast, well-understood toolkit for analyzing linear systems, things like eigenvalues, eigenvectors, modes which we can now apply to understand and predict nonlinear phenomena.
That is a very clever way to sidestep the nonlinearity. What about its practical predictive power and interpretability? Because understanding why a system behaves a certain way is often as important as predicting its future state.
Its predictive power has been demonstrated quite effectively. The source mentions its evaluation on canonical benchmark systems, like the Duffing oscillator and the Lorenz attractor.
Classic examples of chaotic, nonlinear systems.
Right. And learned approximations of the Koopman operator on these systems lead to highly accurate long-term predictions of system trajectories. Furthermore, they allow for spectral analysis of system modes. The eigenvalues and eigenfunctions of the learned Koopman operator reveal the fundamental frequencies, growth decay rates, and spatial patterns, Koopman modes, that govern the system's dynamics. For the Lorenz system, for instance, learned Koopman embeddings were shown to recover the dominant periodicities and invariant manifolds, key structures in chaotic dynamics, using significantly fewer parameters than recurrent neural networks or LSTMs trained on the same task.
Fewer parameters and more insight.
Exactly. And that leads to interpretability. Unlike often black box recurrent models, the Koopman framework facilitates interpretability through eigendecomposition of the learned operator. Those eigenvalues and eigenfunctions give you direct insight into the system's intrinsic modes of behavior. This also allows for explicit control theoretic analysis, which is crucial if you want to design controllers for nonlinear systems in engineering or robotics.
And can this be combined with neural networks, maybe using NNs to find those useful observables you mentioned?
Yes, absolutely. While techniques like extended dynamic mode decomposition, EDMD, are common for learning finite-dimensional approximations of the Koopman operator from data, finding the right set of observable functions, GX, to lift into is crucial. This is where hybrid approaches come in. Neural networks can be used to discover effective basis functions or observables. You might train an autoencoder, for instance, where the encoder maps the high-dimensional state X to a lower-dimensional set of coordinates, Y, the learned observables, and then you learn a linear Koopman model in that Y space. This combines the power of deep learning for representation learning with the linear structure of Koopman theory.
That sounds like a really powerful combination. However, you touched on a potential challenge, finding the right observables. While the source mentions using NNs to discover them, it doesn't really elaborate on how difficult that might be in practice, especially for complex, high-dimensional, real-world systems where you don't know the underlying equations. Is finding good observables still a major hurdle?
That's absolutely a critical point and a very active area of research. It's one of the main practical challenges in applying Koopman theory broadly. For simple, low-dimensional benchmark systems like Lorenz or Duffing, you can often get away with using hand-picked basis functions, like polynomials or Fourier modes, as your observables. But for complex, high-dimensional real-world systems, think climate modeling, turbulent fluid flows, biological networks, maybe even financial markets, designing or learning the right set of observables is highly non-trivial.
The ones that actually make the dynamics linear in the lifted space.
Exactly. If you choose a poor set of observables, the dynamics in the lifted space won't actually be linear, and your learned Koopman operator won't be accurate or provide meaningful insights. Using neural networks, like autoencoders, to find these observables is promising, but it introduces its own complexities. How do you design the network architecture? How do you ensure the learned observables actually lead to linear dynamics? You might even end up replacing one black box, the original nonlinear system, with another, the deep neural network finding the observables, potentially losing some of the interpretability benefits. So yes, efficiently and reliably, finding a finite set of observables that captures the essential dynamics and truly linearizes the system for complex, unknown, high-dimensional cases remains a significant bottleneck and a key focus for future research.
Okay, that makes sense. The theory is elegant, but the practical application has its hurdles. Now, this brings us nicely to learnable spectral models and this intriguing S-sticked VLM. These sound like they aim to blend the strengths of spectral methods with the adaptability of learning. How do these learnable spectral models work?
Learnable spectral models take the idea of spectral filtering we discussed earlier, like in Fourier models, and make the filters themselves adaptive and trainable. Instead of using fixed predefined filters, like an ideal low-pass filter, operations like thresholding or modulation in the Fourier or wavelet domain are parameterized and learned end-to-end as part of the overall model training, usually using backpropagation.
So the model learns its own spectral filters.
Precisely. A common example is differentiable soft thresholding. In standard soft thresholding, you zero out coefficients below a certain threshold and shrink others. In the differentiable version, the output coefficient for it might be calculated as FOOC. Here is a learnable parameterized function controlled by parameters FOOC that determines how much to attenuate each frequency component based on its magnitude Fook. This effectively acts as a tunable denoiser or bandpass filter that learns the optimal frequency response directly from the data for the specific task. It lets the model decide, for instance, exactly which frequencies to keep and which to discard for optimal performance.
And then there's STIC VLM, these spectral dictionary vision language models. This sounds like a direct and fascinating challenge to the standard transformer architecture, especially things like self-attention.
It absolutely is. STIC VLM is a really novel approach. The core idea is to replace standard token mixing mechanisms in transformers, specifically the computationally intensive self-attention layers, with a spectral decomposition.
Okay, how does that work instead of attention?
Instead of having every token attend to every other token, which leads to that quadratic complexity and sequence length, the input representation X, which could be image patches or word embeddings, is approximated as a sparse sum over a set of learnable basis functions, or dictionary atoms, X, A, E, I. These basis functions I might be initialized as, say, Gabor filters, cosine waves, or wavelet atoms, but they are then learned and adapted during training. The coefficients AI represent how much each dictionary atom contributes to representing the input X. The mixing then happens implicitly through this shared dictionary and the sparse coefficients.
And what kind of performance are they seeing? Does this spectral approach genuinely compete with massive state-of-the-art attention-based models like BLEEP2, especially in demanding vision language tasks like image captioning?
The results reported in the source are quite striking. On the standard MS-CoKey image captioning benchmark, STIC VLM achieved really impressive scores. BLAU4 of 39.2, CIDR of a 127.5, SPICE of 27.0. What's particularly remarkable is that this performance closes over 85% of the performance gap to BLIP2, which is a very large and powerful attention-based vision language model.
85% of the gap while being more efficient.
Exactly. And that's the kicker. It achieved this while using 60% fewer parameters than BLIP2 and requiring 2.3 times less peak memory during inference.
Wow, 60% fewer parameters and less than half the memory while getting almost the same performance. That's a huge efficiency win. What are the technical reasons behind that?
The authors attribute these significant gains to two main factors. First, the inherent inductive biases encoded by sparse spectral decomposition. The model is essentially designed to find compact, efficient representations by default, using only a few dictionary atoms to represent the input. This encourages simpler solutions. Second, and critically, it's the absence of quadratic attention complexity. Standard self-attention scales as ON2 with sequence length n. This spectral dictionary approach avoids that entirely. Its complexity depends more on the dictionary size and the sparsity level, which can be much more favorable for long sequences or high-resolution inputs. This bypasses a major bottleneck of traditional transformers.
And it also claims built-in interpretability. How does that work in practice for STIC VLM? Can you actually see what it's learned?
Yes, the interpretability is much more direct than in a standard transformer. You can actually visualize the dictionary atoms, I, that the model learns. Doing so often reveals modality-specific frequency features. For image data, you might see learned atoms that resemble oriented edges, specific textures, or color blobs. For language, maybe atoms corresponding to certain n-gram patterns or syntactic structures. It gives you a direct window into the building blocks the model is using. Furthermore, analyzing the sparse coefficients E for a given input shows which atoms are being activated to represent that input. And thresholding the coefficients acts as a form of spectral regularization, which not only helps performance, but also makes the model's internal workings more transparent. You can see exactly which spectral components are deemed important.
These results really hammer home the point, don't they? These mathematically grounded, operator-based approaches aren't just theoretical curiosities. They're empirically competitive, sometimes even beating state-of-the-art deep learning on efficiency metrics. So the big question then is, how far can we push this? Can these operators actually reason in a more abstract, symbolic way, moving beyond perception and pattern matching towards logical inference?
That's definitely the next ambitious frontier for this entire framework. Can we extend it beyond the traditional signal processing tasks? The goal is ambitious, to build systems that can support compositional inference, symbolic manipulation, and logical deduction. Tasks usually considered the domain of symbolic AI, but doing it within this continuous functional Hilbert space framework.
So bridging the symbolic-subsymbolic gap using operators.
Exactly. In this view, reasoning isn't necessarily about manipulating discrete symbols according to logical rules, but can be framed as the construction of structured operator sequences acting on functional representations.
Reasoning as a sequence of operators acting on functions. Okay, that's still quite abstract. Can you give a more concrete example of how functional composition could represent a reasoning step?
Let's try. Imagine you represent concepts like Socrates, man, and mortal as functions or vectors in a Hilbert space H. The idea is to learn a reasoning operator T, perhaps representing the relation as A, such that if you apply T to the function representing Socrates, F Socrates, the result T of Socrates is very close to the function representing man, F man.
So T encodes the Socrates is a man relationship.
Right, and you could learn this operator T from examples using regularized least squares or similar methods. Now, for operator composition, suppose you have another operator TR1 representing A implies B, TR1 FA SB, and a second operator TR2 representing B implies C, TR2 FB or FFC. Then the composition of these operators TR2 applied after TR1, written TR2 PR1, should directly map FA to FC, TR2 TR1 FA FC. This allows you to build complex chains of logical inference like syllogisms, simply by composing these learned functional operators. It's a continuous analog to rule chaining in symbolic AI.
Okay, that makes it clearer. And does this extend to the kernel methods we talked about with RKHS? Can we do reasoning with kernels?
Yes, it does. In the RKHS framework, you can define operator-valued kernels. These are kernels that don't just output a similarity score, a scalar, but an operator. These can be used to encode relational information, like tuples, subject, relation, object, reasoning over chains, like finding Z such that R1XY and R2YZ then corresponds to composition in the tensor product space defined by these kernels. It provides a way to perform relational inference and knowledge graph completion within the RKHS framework.
And what about spectral reasoning? You mentioned the famous king, man, plus woman, and queen analogy, a classic example from word embeddings. How could that work in the spectral domain?
This is where the connection becomes really intriguing and shows the potential power. In a spectral setting, reasoning can be conceptualized as sparse modulation of frequency components. Suppose you have the spectral representation, e.g. Fourier coefficients x for concept x. A reasoning operator R corresponding to a relation R could act by applying relation-specific modulation coefficients BIC to these spectral components, RFX over AX.
So the relation changes the frequency mix.
Exactly. It selectively amplifies or attenuates certain frequencies based on the specific relation. Now consider the king-man plus woman equal 2 analogy. In embedding spaces, this is vector arithmetic. In the spectral domain, it could translate to a spectral shift. The idea is that the spectral coefficients for queen or might be approximated by taking the coefficients for king, subtracting the coefficients for man, and adding the coefficients for woman, plus woman. This implies that abstract semantic relationships are encoded as structured transformations directly in the frequency domain. It's a continuous, potentially interpretable way to perform symbolic-like manipulations.
That's a fascinating parallel. And finally, how do we actually get the system to learn these reasoning operators or spectral modulations?
You learn them from data, typically data sets of reasoning examples or triples like input concept, relation, output concept. You define a parameterized family of operators, say TR, where key R represents the learnable parameters and R specifies their relation. These operators could be linear maps, learnable spectral filters, or even small neural networks operating on the functional representations or their spectral coefficients. You then train the parameters by minimizing the error between the predicted outcome T, R finput, and the actual target outcome foutput across the training dataset. This system effectively learns the specific transformations required for each type of reasoning step. This unification potential is incredibly powerful. By representing abstract concepts and logical relations as operators acting on functions within a rigorous mathematical space like a Hilbert space, we're creating a framework that could genuinely bridge the long-standing gap between symbolic AI, logic rules, and sub-symbolic AI, neural networks, continuous representations. It offers a path towards AI systems that are both capable of complex reasoning and grounded in continuous data, potentially with greater interpretability and robustness.
Okay, so we've heard about the elegance, the potential for interpretability, robustness, efficiency, even reasoning. It really sounds compelling. Which brings us back to that earlier question. With such clear advantages, why aren't these Hilbert space models absolutely everywhere already? What are the main technical hurdles still preventing wider adoption or stopping them from scaling to every single problem where deep neural networks currently dominate? What's really holding them back?
That's the crucial question, isn't it? And you're right. Despite all the promise, there are several significant practical limitations and challenges that need ongoing research and engineering effort. One major challenge is basis or dictionary selection. We talked about how spectral methods rely on representing functions in a basis, like Fourier or wavelets. But the performance is often highly sensitive to how well the chosen basis aligns with the inherent structure of the input data.
Meaning a fixed standard basis might not be the best language for every type of data.
Exactly. Fourier is great for periodic signals, wavelets for signals with localized features, but what about complex, high-dimensional data, like natural images with diverse textures, or data lying on complicated manifolds or graph-structured data? A predefined basis might not provide a sparse or efficient representation for all kinds of data structures.
So finding the right language or basis for the specific data is key. What are the promising approaches researchers are exploring to tackle that?
The most promising direction is developing data adaptive or learned dictionaries or bases. Instead of fixing the basis beforehand, you try to learn it from the data itself. Techniques include manifold learning, which tries to uncover the underlying low-dimensional geometric structure of the data and build the basis adapted to that manifold. Graph-based harmonic analysis, which develops Fourier-like or wavelet-like bases specifically for data defined on graphs or networks. Or even using deep learning tools like variational autoencoders for basis discovery, where a neural network learns an optimal representation, the basis or dictionary, that balances reconstruction accuracy with desirable properties like sparsity or orthogonality. The goal is to let the data itself guide the choice of the best representational framework.
Okay, basis selection is one hurdle. What about handling truly complex nonlinear phenomena? You mentioned most spectral transforms are inherently linear. How do these models cope when the world isn't linear?
That's another critical challenge. Linearity is often a blessing for analysis and guarantees, but a curse for representing complex real-world phenomena. While Koopman operators offer that elegant way to linearize dynamics by lifting to function space, we already discussed the difficulty of finding the appropriate observables to make that work reliably for complex systems. For other spectral methods, yes, the core transformations like Fourier or wavelet transforms are linear, so nonlinearity must often be reintroduced through auxiliary mechanisms.
Like the modulus operator in scattering transforms.
Exactly. Or using learnable activation functions in the spectral domain, like the soft thresholding we discussed, or incorporating pointwise nonlinearities, or building hybrid architectures that combine linear spectral layers with standard nonlinear neural network layers. The potential downside is that introducing these nonlinearities can sometimes compromise analytic clarity and make theoretical analysis harder again. It's a trade-off. Future work might explore using more inherently structured nonlinear operators like Volterra series or certain types of integral operators, which have a richer mathematical theory than arbitrary deep network nonlinearities. Or finding more principled ways to blend linear spectral modules with nonlinear deep components.
And what about the classic cursive dimensionality? How do these methods scale when you apply them to extremely high-dimensional data, like video streams, 3D medical scans, or complex multimodal signals? That's a bottleneck for almost all AI approaches.
Scalability to very high dimensions is definitely an ongoing concern and active research area. When you move to modalities like high-resolution video, space plus time, volumetric data, 3D, or signals defined on massive graphs, the sheer number of basis functions needed for an accurate representation can explode, leading to prohibitive computational and memory costs for storing and manipulating spectral coefficients, or large operator matrices.
So how can we fight that curse?
Several strategies are being pursued. One is leveraging structured sparsity. If the signal is sparse in the right basis, techniques like compressed sensing, adaptive basis pruning, only keeping the most important basis functions, or using tensor factorizations, like Tucker or tensor train decompositions, can dramatically reduce the effective dimensionality. Another powerful approach is using hierarchical or multi-resolution decompositions. Think about how wavelet packet transforms recursively subdivide the frequency space, or how scattering networks build features hierarchically across scales. These methods break down the high-dimensional problem into a series of smaller, more manageable subproblems, often making computations feasible.
Okay, sparsity and hierarchy. What about modeling systems that change over time or where causality is crucial? Are spectral methods inherently good at handling dynamic or real-time processes?
Not always inherently. Traditional spectral methods are often time-invariant and global. Fourier analysis, for example, assumes the signal's frequency content is stationary over time and looks at the entire signal at once. This limits their direct applicability for modeling systems where properties change dynamically, or where you need real-time processing with low latency, or where understanding temporal causality is key, like in forecasting or control.
So what are the future directions for incorporating time and causality better?
Researchers are exploring several avenues. One is developing time-varying or non-stationary basis functions, like wavelet packets that adapt their frequency tiling over time, or Gabor frames with dynamically adjusted time-frequency windows. Another is augmenting Koopman operator models with time-varying observables or delay embeddings, using past states to predict the future, to better capture system memory and non-stationarity, making them more suitable for forecasting and real-time control tasks. It's about making the spectral lens adapt to the changing dynamics of the signal.
And finally, let's talk practical implementation. Getting these often complex mathematical operations, FFTs, wavelet transforms, operator inversions to run efficiently on modern hardware like GPUs, and integrating them smoothly into the existing deep learning ecosystems, that must be a significant engineering challenge itself.
It absolutely is. It's often the difference between a beautiful theoretical idea and a tool that researchers and engineers can actually use widely. While many fundamental spectral operations like FFTs, some standard wavelet transforms, DWTs, have highly optimized implementations available in libraries like CuffFT or PyWavelets, which run well in GPUs, integrating these operations seamlessly into end-to-end differentiable pipelines within frameworks like PyTorch, TensorFlow, or JAX remains a challenge.
Especially for custom operators or less common transforms.
Exactly. If your model requires custom backpropagation rules through complex signal processing layer, or involves operations not natively supported with efficient gradients, implementation can become a major bottleneck. So a lot of ongoing work focuses on creating optimized GPU-friendly libraries for a wider range of spectral primitives and ensuring they have robust automatic differentiation support. Leveraging tools like just-in-time JIT compilation, like a JOSHIX or PyTorch's Torch script, and sophisticated automatic differentiation systems is key to making these operator-based models as easy to build, train, and deploy as standard neural networks. The tooling needs to catch up with the theory. So yes, these limitations, basis selection, nonlinearity, scalability, dynamics, implementation, they are real hurdles. But crucially, they're not seen as fundamental dead ends. They are viewed as exciting open research questions, and the strength of the underlying mathematical theory, functional analysis, harmonic analysis, operator theory provides a clear roadmap, a set of powerful tools for tackling these practical challenges. The hope is that overcoming them will unlock truly powerful, trustworthy, and efficient AI systems for the future.
And just to add one more layer to that, something the papers often don't discuss explicitly are the non-technical barriers. Think about the existing AI ecosystem. There's just a massive investment in and deep familiarity with neural network toolchains, PyTorch, TensorFlow, Keras. Researchers, engineers, students, they're largely trained in that paradigm. There's a huge community, tons of shared code, pre-trained models, tutorials.
All the infrastructure.
Exactly. Shifting to a Hilbert space paradigm, even with all its elegance and potential benefits, might require a different skill set for many people. A deeper grounding in functional analysis, signal processing, maybe numerical methods, things that aren't always central in a standard data science or ML curriculum right now.
That's a very valid point.
So it's not just about proving these methods work technically, it's also about building the community, the educational resources, the easy-to-use tools, essentially, building a whole new ecosystem around them to foster wider adoption and innovation. Okay, so let's try to bring this all back together. What we've really explored today is this fascinating idea that Hilbert's space-based models offer a fundamentally different approach to AI, one that's deeply principled, inherently more interpretable in many ways, and potentially much more computationally efficient than the dominant deep neural network paradigm. And they achieve this by completely reframing machine learning, not as just tweaking huge lists of parameters, but as performing precise operator estimation and computation within these structured, infinite-dimensional function spaces, leveraging all the rigor of classical signal processing and spectral theory.
That's a great summary. That's exactly right. And their particular strengths really seem to shine in situations where interpretability isn't just nice to have, but essential, where provable robustness is critical, where data efficiency matters. This makes them incredibly promising for applications where we need trustworthy AI, and that's not just a buzzword, but a genuine hard requirement. Think about scientific discovery, advanced medical diagnostics where a doctor needs to understand why the AI suggested something, autonomous systems where failure is not an option, financial modeling where stability is key. They offer a level of analytical guarantee, a potential for deep understanding that is often very difficult, it's not possible to get from purely empirical black box deep learning models.
So as we keep pushing the boundaries of artificial intelligence, maybe the path forward to truly profound, reliable, and verifiable intelligence isn't just about scaling up neural networks to unimaginable sizes and hoping for the best. Hoping intelligence just magically emerges from complexity. Perhaps it also lies, maybe even more so, in deeply understanding and skillfully harnessing these elegant, infinite dimensional structures of function spaces. What new kinds of machine intelligence might become possible when we build not just on brute force empirical success, but on foundations of inherent clarity, mathematical certainty, and provable guarantees? It's certainly a compelling and, frankly, quite different vision for the future of AI.
It is indeed a provocative thought to end on. The future might well be a powerful synthesis, leveraging the best of both worlds.
And if you, our listeners, want to stay updated on the latest AI and ML research papers and continue your own deep dive into these cutting-edge topics, be sure to visit our webpage, neuralintel.org. We're always exploring the frontiers of machine intelligence there.
Thank you for joining us on this deep dive into operator theory in Hilbert spaces.
We'll see you next time.